Street Physics.
This is from 1991, and it's question number 2. I want to give that a try, and then I'll work out the solution here on the board.
Pause the video.
We got some sort of cylinder, and we have another cylinder stuck to the first cylinder. I'm going to draw a side view. They gave a perspective, so you had a good idea what was going on. Well, I have a good idea what's going on, so I'm going to draw a right angles, hard angle, because, you know, the reality is this is a better angle for doing an analysis. What do we have here? We had a block hanging down like that. Two masses, M1 and M2, are connected by light cables to the perimeters of two cylinder radii, R1 and R2, respectively. The cylinders originally connected to each other, but are free to rotate about a common axle. All right, they're stuck together, but there's no friction. The moment of inertia of the pair is 45 kilogram meter squared. Determine M2 such that the system will remain in equilibrium. Well, that looks pretty straightforward. If it's in equilibrium, then the sum of the torques equals 0. I'm going to sum the torques around the axle. That's the only place that really makes sense in this problem. All right, sum of the torques equals 0. All right, so let me actually literally draw a torque diagram. I have this thing. I got the wheel, and all right, for the first one, we're finding the torque about the axle. So my position vector of where the force is acting is right here. There's my position vector R. R, it's kind of little. And then there's a tension force like that. Like that. And there's our tension force. So we got R cross F. That's going to be out of the board like that. R cross F. They're already at right angles, so I don't have to do any fancy trig stuff or anything like that. So we got R cross F is like that. So that would be R1 times the tension. Now, since this is at rest, if I draw a free body diagram, I see the tension equals, I'll call it T1, equals the weight, because it's not accelerating. Usually that's not the case. Don't fall into that trap. It's a sucker's play right there. If you're thinking these are always the same, they're not always the same. They are the same here because it's not accelerating. But, so this is kind of easy here. We got R times the weight of the object, which is going to be M1G, right? So there's our torque due to that. And then our torque due to this one is going to be, here's our R. There's our position vector from the point of rotation. And here's our, I guess I should call that T1. T2, I call it R2. Right? So this is going to give me a negative torque, in this case, or into the board. R2 equals M2, minus M2G equals 0. All right. There's our torque relationship. And we wanted to know what M2 is. So I'll just solve that for M2. All right. Well, the G's go away. All right. So we end up kilograms. 23rd kilograms. 23rd kilograms. All right. So there we go. That was M2. M2 equals whatever that is. 23rd kilograms. All right. Here's the answer for part A. Okay, next. Mass M2 is removed. All right, we only have M1. Determine the angular acceleration of the cylinders. All right, well, I need a torque diagram, I think. All right, we got our tension down like that. And I probably should have drawn the force. The force of the axle is like that. All right, those are the only forces that could, only forces. So let's sum the torques about the axle. Some of the torques about the axle is I about the axle, which conveniently we know, times alpha. All right, we want to know what alpha is. Now, don't be a sucker. Don't be a sucker. Don't say the tension equals the weight. Well, it doesn't. It doesn't equal the weight in this case because this is a different situation. This is accelerating down. Things accelerating down. So we need to take a look at that there. And I'm going to draw a free body diagram again. And we got like that. Here's my free body diagram. I got the weight down, which is M1G. And since it's accelerating down, T1 must be smaller than that. All right. So be careful with that. But anyways, some of the torques is going to be, let's see, we got the T1, R1, and that's going to be positive equals I axle alpha. All right, can't solve that. I want to know that, and I don't know that. So I'm going to have to, sum the forces, I think. Sum of the forces in the Y equal M1 acceleration 1. T1 minus mg. M1g equals M1a1. All right. Now, looks like we don't know the tension, we don't know alpha, and we introduce a new variable. But there's a relationship between A1 and alpha. Let's see. As A1 slides down like that, A1, and that's going to be negative, so I'm going to put a negative there, equals alpha R1, and that's going to cause it to kind of have a rotation like this, which is positive. So negative A1 equals positive alpha R1. Make sure you get those signs right. And I want A to go away, so I'm just going to say T1 minus M1G equals M1 alpha R1, and that is negative, right? So because A1 equals negative alpha R1, right? So we got to put negative in there. All right, well, let's just take that. Just take that right there, plug it into there. All right. This is shaping up to be fantastic. I want to get my alphas together. Let's bring that to the side. All right. So I could factor out my alphas here. And then let's just divide that through. All right. And we have all kinds of values we can plug in there. Let's see, is this making sense? Well, we know that I is going to be some multiplier times mr squared, and this is mr squared. Okay, we can add those together. That's cool, because we're going to end up with mgr over mr squared, right? So the m's are going to go away. That's going to go away. So we're going to end up with meters per second squared divided by meters. So we're going to end up with units of per second squared, which is angular acceleration, right? It's radians per second squared, but radians aren't the dimensional unit. So per second squared is solid. All right. So our units are good. So that's good. All right. So I can just plug some numbers in. 2.2 radians per second squared. All right. So what else? Now we need to find the tension in the cable supporting M1. Well, that's kind of easy, I guess. Once we have that, we just kind of plug that into there. And the tension in the cable is 20 kilograms. That is a massive mass. 20 kilograms. That's a lot of mass. 9.8 newtons per kilogram. Minus 20 kilograms times 2.2 radians per second squared. Times R1 times 0.5. All right, let's see what the tension is. Better get a positive value. Otherwise, I will. I'm feeling pretty good about that. 174 newtons. That's a lot of force, but that's 20 kilograms, so that thing's pulling down with about 200. So, yeah, So the weight was about 200. So, all right, something like that. And then determine the linear speed of M1 after it has descended 1 meter. All right. Since they asked us about the change in position, this is usually going to be most easily done using conservation of energy. We got two positions, 0 and 1, and we could say the energy at 0 equals the energy at 1. This is one way. You can use kinematics too. There would be a number of steps to do with kinematics because of the position thing. But anyways, let's see. So this is going to start up here. Let's say that the gravitational potential energy equals 0 when it gets to the bottom like that. So the this thing starts off at rest and it has some gravitational potential energy due to the height of the block. And then at the end, we got the translational kinetic energy of the block plus the rotational kinetic energy of the cylinder thing. We're going to need to, and we want to know the linear speed. So V equals omega R1. So the speed of this outer portion of the hub is omega R1, and that's also the speed of the block. So let's just flop that out. Omega equals V over R1. V over R1 squared. So we could solve that for V1. Let's put some numbers in. See what we get. Let's see what we get. Where did I put my calculator? Oh no. What can I do without my calculator? Where did I put it? What did I get? 1.4 meters per second. Let's see. Let's try that again. Looks like 1.4 meters per second. All right, that's downward, of course. That's for the speed or the velocity. What did they ask for? Determine the speed. All right, don't need down. All right, there you go. Here's a 19. What year was that? That was 1991. AP problem. All right, there you go. Hope you're enjoying your quarantine. Stuck in the house. I'll try and get one of these lessons out every day. Check which for homework. I'll see you tomorrow.
It's Street Physics.